Hello. Hi, it's a pleasure to be here again. Last time I was here was 2.5 years when I was still doing my PhD in Warwick. So now I will talk about coevolving networks and the different aspects of coevolving networks. Now, specifically, I will talk about the coevolving voter model, which is Fed's model, what happens when we put it on the multiplex. I will also talk about what happens to it when we input some noise, and the last thing that I promised in the abstract, I will not talk about. Because I promised too much, but maybe I can talk about it in the socio meeting. And this is about diffusion in multilayer. So, what is all this about? This is about social dynamics, so how individual actions influence collective behavior. So basically, we're looking for ingredients, trying to understand how what goes in, how human beings make decisions, and how it results to collective phenomena as seen here. For example, this is Via Catalunya. So what we will have is binary state models of decision-making, opinions, and things like this. So this will be the object of study. So what are the mechanisms for state change of these agents? So agents here represent individuals. The basic ingredient people usually put in is the social limitation, so something observed from reality. And the mechanism for that is the voter model. So the voter model, in the implementation that we will be considering, involves picking an individual on the network at random, looking at a random neighbor, and if the state of the neighbor is different, the individual assumes its state. So for example, the opposite would be called the invasion process. So the voter model is nice, and dynamics depends on graph type, update rules, etc. And there are many papers, but here I don't need to explain that to anyone. But for finite networks, such a system will always reach consensus. So networks will always end up either all nodes being red or all nodes being blue. So clearly, it rather limits the range of phenomena we can look at. So what do we do instead? We supplement. We put another ingredient in our recipe. The ingredient is the breaking and establishing ties, so the principle of homophily. That is modeled by rewiring. So now, with some probability, the node, the randomly picked node, will change state. And with a complementary probability, this link that joins together two nodes that kind of disagree will be rewired to a node that is in the same state as the initially picked node. So these are the two mechanisms. So thus, dynamics on the network becomes coupled to the dynamics of the network. And the graph evolves simultaneously with the states. This is the coevolving voter model, which is this paper here. What happens to it? What are the consequences? Well, in the general voter model, you will see consensus after a while. Now, what happens in the coevolving voter model would depend on this parameter P, which is the plasticity parameter, which measures the balance between the timescales on which nodes change state and the timescales on which nodes rewire. So if you have a lot of social limitation and not so much rewiring, you still reach consensus. On the other hand, on the opposite extreme, when you have a lot of rewiring, and so this is breaking and establishing ties, symbolized rewiring, and not so much social limitation, the network will fragment into two components of equal size but opposing states, which means that somewhere in between, at the critical rewiring parameter, you will see a transition. This transition is called the fragmentation transition for finite size systems, and it tells you about the final state of the network. So here you have two potential states, and this is a graph from Fed's paper. What it means is that if you trace the largest component, it will shift from 1 to 0.5 at some critical rewiring parameter. The other thing that happens in this model is the absorbing transition, which coincides with the fragmentation transition. So whereas the first tells you about the state of the network, the second tells you about the activity of the system. How do you measure activity? Let's say this is a network. What you look is at the relative number of links joining together nodes in opposing states. And you divide it by the total number of links, and what you get is something called interface density, so the density of interfaces or the density of active links. Here, for example, it will be 5/8. So what you do is you average over many realizations in the ensemble, and with time, you see that this average interface density either stays a finite amount at a finite value, or it goes down to 0. What it means that here the network is active, and here the network is frozen. okay? And the transition between activity. And when you look at the asymptotics, what you get is this curve here. So each value here, each point here is the value of the asymptote here. So as you see here, at this critical P, around 0.4, you will have an absorbing transition. So for small rewiring, network will be active, and finite size networks will freeze in one component. And for rewiring greater than critical value, networks will be frozen, and it will freeze into two components. So you don't have to have consensus anymore. You can have coexistence of opinions. Okay, and actually this fragmentation transition is a generic phenomenon observed as long as, well, not as long as, but observed in many models where the dynamics on the network corresponds with the dynamics of the network. So it's not just in that model. You also observe it in the Axelrod model. I'm sorry for the green. You can't see it. So what do we do? This is what we had before, Coevolving Voter Model. The extra ingredient we add in the context of the program in which I'm paid is the multiplex. So the extra ingredient is the context. This recognizes that in some context, for example, family, you're much more likely to change your ties than in other contexts. So for example, work. Okay? So what we will, this is the multiplex paradigm. So you join together two networks. Multiplex is a very, well, there isn't really a consensus about what it means. So this was a paper, this is a slide from February. In February, this paper was in the 3rd edition reviewing the multiplex paradigm, and it gave 300 references. This basically shows that there are so many names for coupling together two networks, and the authors try to understand what names correspond to which aspects of coupling. I don't think there is a, and this was a paper from half a year ago. The context in which we will be using it, however, is that nodes represent agents and layers represent context, which means that if there is a link between two layers, it means that a node exists in both contexts, which means that you can have at most n interlayer pairwise links. And networks will be equal size, and the node states, if they're connected, have to be the same. So I want to preempt the potential question of why we're adding this extra ingredient of multiplexing. We're now working with people from Vienna who are analyzing the data of the Bardos game. So it's a game where you walk around and you can establish different sorts of ties. Like, for example, you can send a message to someone, you can trade with them, you can have negative kinds of ties. And when you look at the ties as representing networks, you see fragmentation. So you do see the kinds of behavior that we will be observing in our models. So it's not that random. Okay, so what do we have? We have a multi-layer coevolving voter model. We have a rewiring rate P1 on layer 1, a rewiring rate P2, and we control for the number of agents that exist in both levels. We call this the degree of multiplexing. Okay, it's a parameter Q. So Q can vary from 0 to 1. If it's 0, you have two disconnected networks. If it's 1, you have a fully connected multiplex. The evolution is that you pick a layer at random, you evolve it according to the coevolving voter model I've shown before. So the node can either change state or change a tie. And if at the result of that update the node changes state, and if it's connected to another layer, then the state change propagates. So in this way, you have one layer influencing the other layer through the changes of state happening on one of the layers, on either of the layers. What do we see? Well, if you just connect two voter layers, two voter models together, what you see is that this is the so it measures activity. This is a disconnected multiplex, and this is a connected multiplex. So the first thing you see is that when you connect layers together, there is more activity. And on the other hand, the time scales are much smaller. So the system reaches the asymptotic level faster, and it escapes from it faster. And when you look at the asymptotic values of these, what you see is the shift in the transition. So these are results. Now we can vary P. Before, in the previous slide, it was just for P equals 0. So this, for Q equals 0, is the asymptotic interface density for the monoplex, which is what we saw before. This is a known result for the Coevolving Voter Model. In black is the fully connected multiplex. And we see that the transition that before happened here is shifted to high rewiring, which means that multiplexing shifts the absorbing transition, and the absorbing transition still exists. The equivalent to the absorbing transition is the fragmentation transition, which once again in this multiplex system coincides with the absorbing transition. So now for a larger rewiring rate, you can have systems freezing in one component. And then over here, both layers will freeze in two components, obviously fully connected to each respective component. So you have coexistence of opinions on both levels. And the critical rewiring shifts with multiplexing. So this is a result for identical layers. And also, once again, we have the critical slowing down indicative of the transition in the multiplex, which is shown here by the peak and the characteristic times. We can write equations that explain this shift. So here we write equations for the interface density using a mean field pair approximation. And what we get is this. So this is a PQ surface of the of the active state, and this is predicted by the equations. Okay, so when you collapse it onto, when you just look at Q equals 0 and Q equals 1, so this is analytics, and you see the shift in the absorbing transition, and this was numerics. So qualitatively, analytics do a good job at explaining what's happening. And it's very easy to ask the question, well, okay, if you have two identical layers with identical rewiring rates, because that's what we've been looking at, is it actually just one layer rescaled? Do we need the multiplex paradigm here at all? Because the monoplex with degree, k is degree, 8 actually is asymptotically the same as a fully connected multiplex with degree 4. So maybe they are the same. And we show in our paper that indeed, when this layer has the same rewiring as this layer, the equation for the monoplex, for the asymptotic interface density, the change, is an equation, a rescaled equation, the equation for the multiplex is a rescaled equation for the monoplex. So what you need to do is rescale time and rescale the effective degree, right? Because now nodes which exist both here and here, they will have some neighbors here and some neighbors here. So you need to account for that. And when you put this mu effective into the monoplex, you can get an equation. So, for example, this is a trend predicted by the monoplex for the variation in the asymptotic interface density of the voter layer as you increase the number of connections between the layers. And you see that this trend actually does a nice job of following the numerical results here, numerical results for the monoplex. But you have to be careful, because not always is the multiplex the same as the monoplex. If you take this layer to be identical to this layer, identical in the sense that there is a perfect edge overlap, then this correspondence is no longer true, because you will need probably a different rescaling for degrees. Also, the correspondence is no longer true when you look at timescales. So the trend that we see of character versus Q is in circles is different to the trend predicted by, so this is a prediction for the voter layer for a monoplex. And that doesn't correspond. So we can't just plug an effective degree into whatever we want, Weaver, and get the same as the monoplex, as the multiplex. So coming back to the multiplex coevolving voter model, we can look at the asymmetric levels. So now, what's happening here, the rewiring can be different to what's happening here. So why we initially started looking at this. And this is a phase diagram from analytics. So this is P1, this is P2, the rewiring probabilities of two levels. And this is a interlayer connectivities. So here we have a disconnected multiplex. So here layer 1 is active, layer 1 is frozen, layer 2 is active. So this is basically a two-dimensional version of what you knew before. On the other hand, analytics say that when we increase Q, so when the moment we have even one link between two layers, they say that it is enough to keep both layers active. Okay, because yeah. So for example, if you look at, I don't think you can look at white plots here because it's hard to see. Okay, but that's what analytics predicts, and it also says that interface densities need not be equal. Okay, and how this is shifted to that is the symmetric multiplex behavior we saw before. Okay, so and we always have maximally one stable active solution. So for that, analytics is good as well. So this is to do with the absorbing transition. And now let's look at when we have different layers and how they fragment. So what we look at first is at the extreme. Here we have a layer that can only change links. Here we have a layer that can only change state. So this is the extreme. This is the topologically dynamic layer, and this we call the voter layer because it has no rewiring. And we control for the number or the fraction of connections between two layers. Of course, this layer will receive state updates from the bottom layer, right? But the opposite will not be true. So actually, causality will only flow upwards. So here, there will be no change of state happening by itself, which means that this layer will not have any information from the top layer, and it will not fragment. So let's look at what happens. So this is disconnected multiplex. Okay, so this is voter, it should not fragment, and this layer should fragment. And when you run, indeed, very fast, the frozen layer becomes frozen and fragments, and the voter layer takes, well, order n time to reach the absorbing state. Okay. And now let's join two layers together so that every second node is connected. So we see the voter layer is not fragmenting, but something strange is happening on the topologically dynamic layer. So these are two clusters, and they're trying to separate, just like before, into two components. But it takes a very long time, and when they finally succeed, it is at the expense of many, many isolated nodes. Now, these nodes are isolated from each other, but they are connected to the other layer. Okay? So what we see is one component, two component. This component looks smaller because of the way network is visualized. It's to do with the spring layout and the density of links. But actually it will be, let's say, roughly or maybe slightly smaller than this. Okay? And you have many, many isolated things. So this is the picture that we saw there. What's happening? When we look at many realizations and we try to get a PDF of the sizes of the first, the second, and the third largest clusters, we get something like this. So the size of this cluster, connected component, it varies significantly. The size of the second largest component, it's a Gaussian. And the rest is basically isolated nodes. Maybe some of them are joined to each other. So whatever the realization, you will only have two significant components and a lot of isolated nodes. Let's try to understand what happens when Q is varied. So before we had Q.5. Now we look at Q ranging from 0 to 1. There are two quantities that we use to characterize this. One is the size of the first and the second largest component. And the second is the relative number of connected components. By relative, I mean divided by system size. Okay? So what we see here is that, so this curve is for 250 nodes, and the other orange curve is for our largest system size. So let's look first at n equals 250. What we see is that as you increase Q, the largest component decreases in size until it completely increases in size. And the second largest component will decrease in size, and you can actually predict how it does so. It's because the second largest component consists of nodes that are not connected to the other layer, and they're in some particular state, which is, well, here you have nodes that are red, some nodes that are blue, right? So half of the red nodes or half of the blue nodes that are not connected to the other layer will end up in the second largest component. Okay? As Q increases, what you see is that the number of isolated nodes grows proportionally to Q. Okay? And you can actually control how many isolated nodes you get by controlling the amount of links between layers. So as n goes to infinity, so now we look at this curve here, S1, well, the two largest components, they're essentially equal size for larger and larger range of Q, which means that they will be the ones disconnected to the other layer, and that the isolated nodes will be the ones that are connected to the other layer, and there will be Q of them. Okay? So what you do by varying Q is you cause the dynamic layer to produce an explosion. So the moment you connect a node, you know it will have to be isolated in the infinite system size limit. So this is something that we call shattered fragmentation, and we describe it in terms of the difference between the sizes of the two largest components and the number of isolated nodes. Why is this a good measure of fragmentation? This is 1 if there is only one component, right? And this is 0 if there are at least 2 equal-sized components. Okay? So, and as you take system size to infinity, the variation of this with Q becomes a step function. So, for example, this is the asymmetric case we saw before. Delta S is 0, and then delta S becomes 1. So you go from a fragmented network to a non-fragmented network. Okay? And the step where this happens, we call it critical degree of multiplexing. So this critical Q, at which the step happens, is the minimal interlayer connectivity that is required for the more topologically stable level to stop the fragmentation of the more topologically dynamic level. Yes, and what we show here is that just because something fragments, we don't really know how it fragments. So how it fragments is told by the number of components. So you can have delta S being 0 and only 2 components, and you can have delta S being 0 and a huge proportion of fraction of components. So this corresponds to the shattered fragmentation case. And this is a plot just to convince you that it's not a consequence of extreme asymmetry. That this happens, this strange behavior of shattered fragmentation will happen as long as the rewiring here is sufficiently different to the rewiring here. So these are plots happening at this star here. Again, you see the shattered fragmentation on the dynamic level. So as long as time scale here is different to time scale here, you will see something of this nature. And this is the last plot on this topic. So you can see how it changes. So you can characterize the shattered fragmentation as the asymmetry between layers decreases. So for example, this tells you about whether a layer is fragmented or not, and this column tells you about how the layer is fragmented. And we can, for example, look at the bottom row, which says what happens as you connect the fully dynamic layer to a voter layer, but then you change. You change the P here, you lower it slightly. Okay? So as you lower the rewiring probability of the dynamic layer, the critical multiplexing decreases. Okay, so you don't need quite so many connections to stop the layer from fragmenting. And what we also see, and this is the main result, is that at subcritical multiplexing, we have this shattered fragmentation. So the strange fragmentation phenomena happens at subcritical connectivity between 2 layers. So this is the end of this work. So to summarize, what we saw is that multiplexing can prevent fragmentation. You have 2 identical layers, but not only. We have a critical degree of multiplexing, so this is the fraction of interlayer connections necessary to do so. And we found the shattered fragmentation. So when you have slightly less connections, the more dynamic layer will split into a multiplicity of isolated nodes and, well, 2 components. And this is the paper that came out recently. And now I will show how this can be explained, how the shaded fragmentation, that it's a consequence of node state being updated as a result of existence of 2 different timescales. So we go away from the multiplex at this point. And we look at Coevolving Voter Model, so single network, and what happens when you throw noise into it. Do we still see the absorbing and fragmentation transitions? So going back, before we had the ingredients of social limitation and homophily, and now we input the extra ingredient of free will, or if you want to be less controversial, of some exogenous update of state. So this is noise. Okay. Some motivation for this. How will we model this? Noise will be a change of state at the end of whatever process will happen to a node. Okay. So you decouple noise. Well, you decouple that change of state to what's happening in the network. So it's some external influence, or alternatively, very internal influence. So you can say that nodes are more individual and less concerned by circumstance and things like this. Alternatively, Kierman, in the paper called Ants, Rationality and Recruitment, so a range of things, he called noise, here he uses the word self-conversion, can be thought of as either due to the arrival of some news or the replacement, basically, of a node by something else. Okay? So what we'll look at here, we can think of as some nodes being randomly replaced by new agents. Okay? Not necessarily as some change of state. So the question is, do we observe the same transitions? And noise and coevolution has been done previously in this paper by Santola and everybody else. So how do we model noise? So we introduced the targeted noise model. So we do it in a very specific way. What we had before was the Coevolving Voter Model. What we do now is we designate a fraction Q of nodes as being susceptible to noise. What you do is you designate those nodes in the beginning of the simulation. They will never change. That fraction, and not only that fraction, those specific nodes will always be the same. Okay? And Q will measure that fraction. Okay? And we will say that those nodes can assume a random state with probability epsilon. Okay? So to evolve, you pick a node at random. You evolve according to the Coevolving Voter Model rules. So at the end of this, maybe node state change occurs. It doesn't matter. The node has been picked. And if the node was a noisy node, then you change its state with probability epsilon over 2.
What is noise? Change state or assume a random state?
Okay, so epsilon is assume random state, which means epsilon over 2 is your change state. Epsilon is the probability to assume a random state, which means that with epsilon over 2, you change state. So we use this. Okay.
Depends on the density of, you have more of one state than the other, and you will have more frequent changes from one type to the other than the reverse.
Maybe. This is what we use in simulations in practice. You change it.
For the aficionados to Monte Carlo, because the heat bath and the if you change the state, or you assume a random state, this is not the same. Well, for many things it's the same, but not for others. So you are changing the state before.
Yes. Okay, I need to think about that, but yes, what we do is this. Okay, so there are 3 parameters. Just that should be here, maybe. Epsilon over 2. Then Q, the fraction of noisy nodes, and the rewiring probability. And we see what happens as these parameters are changed. And we use the standard random regular network of size n and average degree mu. There'll be 2 cases of this. If all the nodes are targeted, then it's basically, we call it homogeneous noise, which means that all nodes can change state with probability epsilon over 2. Okay? And the other extreme that we look at is we target. So we pick a fraction q, but then we say, okay, if you're part of that fraction, then you will definitely, well, you will change state with probability epsilon over 2. So we keep epsilon fixed at 1, okay, here. So there are two extremes. So what happens first in the homogeneous noise case? This is the simulation. So this measures activity as a function of rewiring and noise intensity. So over the coevolving voter model. So here you would be active and here you would be frozen. We see that there is always activity as long as there is noise, which makes sense because absorbing and topologically absorbing states no longer exist, right? Because always some node, any random node, can change state, which will correspond to a link suddenly becoming active, which will trigger things in the system. Okay? And the intensity of this activity increases with epsilon and with p. Okay. And it corresponds very well to the pair approximation. So you can understand this change of activity by writing equations for rho. And you don't need to rescale it by survival probability anymore to get the same values as you did in the CVM because there is no death. All realizations are active. Okay, so basically homogeneous noise destroys both the absorbing and the fragmentation transitions. And here the system will always be in one component. It won't suddenly break and recombine. It will be in one. Then some more interesting things will happen here, but we're not going to go into that because now we'll talk about targeted noise. There's not enough time. Okay. So we're now going to contrast the situation here, the activity here, and the fragmentation here to what happens when you target noise. Okay? So this is the fragmentation phase diagram that we try to draw. This is extent of rewiring P. This is now not epsilon, but rather Q, the fraction of targeted nodes. So this is the coevolving voter model. Here you have both absorbing states and topologically absorbing states because there is no noise. This is the this is the voter model with targeted noise, which is the targeted noise equivalent of the Kierman model. And here everything is basically, topology can't change, so you're trivially in a topologically absorbing state, but of course you're not in an absorbing state because states of nodes will change. In fact, everywhere here there will not exist an absorbing state. Of course, somewhere you will have topologically absorbing states. So even though noisy nodes will be able to change states, topology may end up being fixed. And this is what we'll be interested in. So the only topologically stable configurations under targeted noise are such where the noisy nodes are completely isolated and they're not able to influence the links. Okay? They're not able to make the frozen links active anymore. Okay? What happens to the rest? What happens to the normal nodes? We don't care. But we know that everywhere here, you need to have at least Qn isolated nodes. Okay? Except for in a small region where there aren't enough normal nodes to hold all the links. So there is a sort of maximal fraction of noisy nodes you can have before the normal nodes will become saturated with links. And you'll have no absorbing state. So if you target too many nodes, the system will always be active. Okay? And this happens, this region does not exist in the thermodynamic limit. Because this line is Qmax here, and it's inversely proportional to n. So let's look at what happens when at the absorbing, well, when the system has reached an absorbing state. So this is the coevolving voter model. For high rewiring, you have fragmentation in two components. Now, let's target some proportion Q of nodes with noise. What you will have is something like this. Is the topologically absorbing state. You will have Q n nodes being separated, And the rest, the normal nodes, will split into two components in opposing states. And the states of these isolated nodes will keep on changing because they're still subject to noise. Because noise never stops. It doesn't stop when you reach the topologically absorbing state. So here we know that Qn nodes and at least two giant components. Now let's look at the other side of critical rewiring. In the normal coevolving voter model, you will have network not being fragmented. So you will have the network reaching consensus. But when you add the same proportion of targeted nodes, if you try to see what this picture is for the same system size, you can't. Well, you probably can in very, very large time limit. So you run a system and you look at it after a very, very long time and you see it hasn't fragmented yet. It hasn't rather reached an absorbing state. Because here you don't have Qn isolated nodes. You have basically some red nodes covered by yellow nodes and they're all in one component still evolving. So we can look at a smaller system size. So we can look at a system with only 25 nodes. And yes, so we see here that it has reached a topologically absorbing state with Qn isolated nodes and only one, not two, giant components. Okay? So we begin to see how this consensus versus two components becomes translated as you increase, as you target. Okay. This will maybe take a while. Okay. We need to characterize this somehow. Okay. So those 3 points, those 2 points, plus a third point. So this third point is located in a region where a system is always active. Let's see what happens to those 3 points as samples of the phase space. This informs on activity, and this tells about the fragmentation. And this is the variation of parameters of some quantifiers with time. Okay? So let's look at fragmentation first. We see that both A, so here, the largest scales as 1 minus q. And B, the largest component, scales as 1 minus q over 2. Now, it does not mean, but we infer that here you have one large component and here you have two large components. Okay? And correspondingly, at both A and B, so here you will have the NC, so the number of isolated nodes, here we divide it by Q, being 1, which means that the number of connected components, which is roughly equal to the number of isolated nodes for a large system size, it scales with Q. Okay? And gamma, so this region here, there is once again no dynamic fragmentation recombinations, just one component, and no isolated nodes. And when you look at activity, you see that B, a system in B, will become frozen. So interface density, average interface density, goes to 0. It doesn't go to some finite limit. We've seen before it can happen. Also, gamma is always active, roughly 0.5, right? So there's basically just randomness in the system and one component, and nodes change state all they like. And so gamma and beta are plotted for 250 and 500 nodes. When you try to see what happens to alpha, you realize that for the system to reach an absorbing state, for a system of 25 nodes, you need to go to 10 to the 6. This is a very large number comparatively, very large number of time steps. Of course, all the time steps are already rescaled by n, which means that system, and it increases as n goes up, which means that here, what may happen is that in the thermodynamic limit, you'll have an active system. And these active systems will be characterized by very long lifetimes. Okay, they won't scale with n anymore. The characteristic times will scale faster than n.
One question.
Yeah.
In the largest component, in the middle figure,
Yeah.
the alpha goes to 0.8.
Yes.
With size going to infinity.
Mm-hmm.
But the beta goes to 0.45, which is not 0.8, 0.4 that predicts the formula. No, here in the middle one.
Ah, yes.
That is 0.45,
So,
but the formula gives you 0.4.
So system size increases from dotted line to straight line. What's the thermodynamic limit? So we see that it does go to 0 as n goes to. Yeah. Okay, and so finally, let's try to characterize this. So where is this difference? Where is the line, the transition between something represented in alpha and something represented in beta? When we try to look at final states of the system, we need the system to reach absorbing state. When we look at the average time until absorption, we see that there is a transition point where it basically becomes very, very large. Right? So here systems reach absorbing state in some normal predictable time, faster than n, but suddenly the characteristic time is off the scales in this region. Right? So here it's because there is no absorbing state, fine, but here there is an absorbing state. So it's hard to understand what's happening here as the system, well, as the system will reach the absorbing state. So what we do is we look at very, very large time, and we only try to understand what happens in this region. And in this region, in the red region, characterized, well, represented by beta, we see the shattered fragmentation. This is a number of components. So you see there's a nice correspondence between the legend and here. So the number of components grows with the targeted fraction, and size of largest component decreases. And it basically scales as 1 minus q over 2. So there'll be 2 components. So this will be the frozen region that fragments, when it does, into 2 components, and q and isolated nodes. And this is the shattered fragmentation we saw before. And let's look at activity. So we'll talk about this in a sec. Let's look at activity. So before it was fragmentation. When we measure the asymptotic interface density, we see that here it's 0. So the systems which fragmented into 2 components are frozen in the thermodynamic limit, whereas here activity is finite. So this informs on activity. If you then look at, for example, the timescales, we see that the plots we saw before, they coincide. And when you try to understand what's happening here, so when you slowly move from that region up and look at what happens when systems do reach the absorbing state, you see that just as time explodes for them to do so, they end up freezing in 1 component. So just by circling that region and by looking at small system sizes, we can infer that here, the active region will freeze in 1 giant component and Q in isolated nodes. And here, it will freeze in 2 giant components and Q in isolated nodes. And here, the active region with no fragmentation, but it will not exist in the thermodynamic limit. So once again, the absorbing and fragmentation transitions coincide. And we can, okay. We can understand this by writing equations. The interesting thing is here is that rho equals 0 does not anymore correspond to the topologically absorbing state, because, for example, look here, all the links are frozen. They connect nodes with the same state. But because some of those nodes will be targeted nodes, they will change state suddenly, and then this link becomes active, and then topology will change. So previously, what we had is that topology is stationary when rho was 0. But now, we need to supplement the condition for a topologically absorbing state with the condition that all the links are between non-noisy nodes. Okay? Before, there was no separation in link types. And so that's exactly what we do. We write equations for different link types. So, for example, we can have links that join together normal nodes. So like this, for example, and this. We can have links that join together noisy nodes. So only one here. And links that join together normal nodes and noisy nodes. So there are quite a lot of them here. Okay. And obviously, each can be frozen or active. Okay. And then the topologically absorbing states happen when when there are none of these links, and all the links are here and are frozen. In other words, you can have a system being described by a 6-dimensional interface density that talks about different types of links, active and frozen. And so n means links joining together normal nodes, random nodes, or normal and random nodes, in other words, mixed links. Okay? And then when you look at the evolution, well, when you look at asymptotic behavior of this, it should tell you what happens to the absorbing and fragmentation transitions. So you look at the homogeneous pair approximation, and you end up with 6 different equations. They're nonlinear, they're quite horrible. But what they say is that, okay, they're independent of n, and they're valid in the thermodynamic limit. So they ignore the saturation effect. Normal nodes not being able to hold all the links. Here they can, because it's infinite n. What we see here is that this solution, so 1 is in a position where all nodes are frozen and where all links are frozen and between normal nodes. Okay? This solution is always a solution, and this is the solution that corresponds to shattered fragmentation. Okay? Now, you can look at limits, so you can say, okay, you can ask what happens at q equals 0 or q equals 1. But let's just go back to the general case of q and p being in the middle of that quadrant we saw earlier. This is the result. So in this region here, you will have 2 solutions. You will have the solution corresponding to shattered fragmentation, so topologically absorbing solution that we saw, and one other solution, which is drawn here. This is the activity level, okay? In some variables, that is a combination of the 6, okay? And here, at large p and some q, this active solution will no longer exist. So you will only have the solution corresponding to shattered fragmentation. So here is the absorbing transition in black. And this is the results from simulations, which means that this absorbing transition we see is quite nicely explained by this analytics performed using separation of links into different types. So this explains the absorbing transition. And finally, what it explains is the density of, it puts here, the only solution is the shattered fragmentation solution with at least qn isolated nodes, which puts a lower limit on the number of isolated nodes, and indeed the numerics correspond to the limit. So analytics help us in understanding how critical rewiring changes with targeting. They also help us in understanding the nature of fragmentation when the systems will become frozen. So to conclude, when we considered noise in the CVM, so the second part of the talk, homogeneous noise transitions are not robust. Absorbing and fragmentation transitions are not robust to this kind of noise where everybody is subject to it potentially. On the other hand, if you have targeted noise, the transitions are still there. They once more coincide. And networks freeze into either 1 or 2 giant components and queue and isolated nodes. So in other words, just I want to give some intuition. If you throw some noise into the system, independent of how you do it, to everyone or to some targeted fraction, the network will be active. If you have high rewiring, if everybody will be subject to noise, the network will be active. But if you target and you don't target enough, network will freeze. Okay? And this is what we're finishing now. So to conclude the general talk, coupling networks preserves the transitions, so coupling to identical networks. If topological timescales are very different, so if you have one layer here, timescales are different, you'll see shattered fragmentation. We saw that this shattering of the network doesn't have to be in a multiplex. It can also be observed if you only have one layer, but some nodes are subject to noise. So here we explored the plausible mechanisms of why some real-world systems fragment in the way they do, not just in 2 components. Thank you. Yes.
So you add some noise to the system, then the fragmentation transitions disappear. There is no fragmentation. So can you look at different system sizes? Sometimes this transition fragmentation depends on how big the system is. So
Yes, I would expect that how big the system is would be the same question as how small the noise is. So yes, if you look at very, very small noise, you'll see something like we see in the Kernel model, where you have the transition fragmentation. Well, you have an equivalent transition of the fragmentation equivalent to the kernel happening at larger wirings. So yes, you'll probably see that, but it'll be a balance of system size and the noise intensity.
okay, so the critical noise depends on how the system size is, how big it is.
Yes.
More comments, questions, suggestions? Were you exhausted of the possible? Okay. Okay. So, no, thanks again, Marina.